All right. We're going to talk about spherical coordinates, triple integrals in spherical coordinates. So let's remember spherical coordinates. Just a reminder how they work. X equals rho sine phi cosine theta. Y equals rho sine phi sine theta. And Z equals rho cosine phi. Or I'm sorry, cosine theta. And rho is greater than or equal to 0. And rho is our distance, essentially our distance from the origin. Theta is the same as in polar coordinates or cylindrical coordinates. And phi is measured from the positive z-axis. And this, I realize this should not be cosine theta, this should be cosine phi. Positive z-axis. And phi is between 0 and pi. So those are our conversions for spherical coordinates. So what we're gonna do is develop our triple integrals in spherical coordinates just like we did for cylindrical coordinates. So we're going to come up with a spherical volume element using these ideas, and then we're going to integrate that volume element over our region. So let's draw a picture of our volume element and figure out how we're going to represent it in spherical coordinates. So what I'm going to do with this is we're going to come up here like so. And my little element of volume is going to be here. Like so. And so there's my little spherical volume element. This distance here we're going to call delta rho sub I. So I'm just going to label all my parts here. Delta rho sub I. This arc in here is going to be rho sub I delta phi sub I. This angle is delta phi sub I. And I did my phi backwards here. There we go. Delta phi sub I. The radius here is rho sub I. And where the angle here, that angle is phi sub I. We're going to have a lot of parts here. And we're going to project this down into the xy plane. So if I project this down, here in the xy plane we have a little section, this radius in the xy plane, r sub I, equals rho sub I sine phi sub I. And this arc is r sub I delta theta sub I. And if I do my conversion, that's rho sub I sine phi sub I times delta theta sub I. So I think I've got all the parts here. Oh, and this arc is the same as this arc here. So this side of my little volume element is rho sub I sine phi sub I delta theta sub I.
Where's delta?
Delta theta is right here. All right, now I have all my parts. So we're going to put all these together so we have the sides of this little volume element. This piece is rho sub I sine phi sub I delta theta sub I. This side is rho sub I delta phi sub I, and this side is delta rho sub I. We're going to treat this essentially as a rectangular prism and find the volume, sum the volume of all of these little volume elements over our region. And if we were being a little more precise, we would do like we did in polar coordinates, and we would use the average radius and say the average radius as our delta theta, delta rho, and delta phi get smaller and smaller. The average radius becomes the radius of that little region. So we're being a little loose with how we're doing it. We're just getting a general idea of how we develop this volume element. And all of the arcs, the pieces here come directly from our conversions from rectangular to spherical coordinates. So we're going to take our volume element, so the delta v sub I of this little volume element equals rho squared I.
Is that rho sub I? Or is it just rho?
Yeah, rho sub I. Rho sub I squared sine phi sub I delta rho delta phi delta theta, and these are all sub i's. So this is our volume element, and we're going to sum these over our region and take the limit as the delta rho, delta phi, and delta theta go to 0. So our triple integral in spherical coordinates becomes over our region, call our region Q of f of x, y, z, equals the integral from theta 1 to theta 2, the integral from phi 1, phi 2, the integral from rho 1 to rho 2 of some f of rho theta phi, or sorry, rho phi theta, and our volume element is rho squared sine phi d rho d phi d theta. And this entire quantity is dv in spherical coordinates. So in polar coordinates, we had r d theta. In spherical coordinates, we have rho squared sine phi d rho d phi d theta. That's our volume element. That's always our volume element in spherical coordinates. We can talk about different orders of integration, just like we did with our other coordinates. We have 6 possible arrangements of the d rho d phi d theta. Usually you're going to, this will be the normal or the more usual order of integration when you're using spherical coordinates. And spherical coordinates, we're going to use them when we have spherical symmetry about the origin. So some kind of region where we have spherical symmetry about the origin. So questions on how we developed our volume element. We're good? Same argument that we used for polar coordinates, same argument that we used for cylindrical coordinates. We're just using polar coordinates. So let's do a couple of examples. We're going to redo the example we did yesterday using spherical coordinates. So our example yesterday was the volume under x squared plus y squared plus z squared equals 4, and above z squared equals x squared plus y squared. So we did this one with cylindrical coordinates yesterday. We decided that our region that we're looking at, if we sketch it out really quickly, is we have a cone and we have our sphere above it like so. So we're finding the volume of the ice cream inside our cone. And the sphere intersects the z-axis here at z equals 2. And we'll just look at the first. Well, yesterday we looked at the region in the first octant. Now hopefully this will illustrate why spherical coordinates are really nice. So we need to represent the sphere and the cone in spherical coordinates. So x squared plus y squared plus z squared equals 4. What is, in spherical coordinates, what is x squared plus y squared plus z squared? Rho. So this is rho equals 4. And on the sides of my cone, for z squared equals x squared plus y squared, what equation represents the sides of the cone in one coordinate plane? So if we let y equal 0, I get z squared equals x squared, or z equals x, or z equals y on the sides of the cone. So in spherical coordinates, z equals x or z equals y, how would I represent that? Rho sine phi, what? On the line y equals x, in the xy plane, on the line y equals x, theta equals what? Pi fourths. So in spherical coordinates, the line z equals y or z equals x tells me that phi equals pi fourths. I'm pi over 4. I'm at an angle pi over 4 from the z-axis. So phi equals pi over 4 on the sides of the cone. And going all the way around the z-axis, theta varies from what to what? 0 to 2 pi. So here's one nice thing that's nice about spherical coordinates. I don't have to project this region into the xy plane and figure out the region in my xy plane. I can just look at the region that I'm interested in and translate that into spherical coordinates. So my volume becomes, we've just figured out our limits, theta equals 0 to 2 pi, Phi goes from 0 down here up to my sphere. So, or I'm sorry, that's rho. Phi goes from 0 to pi over 4. Rho varies from 0 to 2. This is rho squared equals 4. Should be rho squared equals 4. Rho varies from 0 to 2. And my volume element, rho squared sine phi d rho d phi d theta. And this integral is about as easy as integrals get. Yes?
So, can you only find rho if you have the equation?
Well, you have to come up with some kind of expression for rho. So you'd have to be able to figure it out somehow.
So rho on this graph is from where t is.
Right. It goes from 0. So if I'm adding up little pieces, rho is 1 here. Here rho is 2. Or I'm sorry, rho is 1 here, and it goes all the way up to rho equals 2. So inside here, rho is going to vary from 0 to up to the sphere. So 0 to 2. But sometimes it might be rho might be a function of phi. It might be a function of theta also, and then you'd have to take that into account when you set up your integrals. And we decided yesterday, when we evaluated this, that came out to, what was it, 8 pi over 3 times 2 minus square root 2. I think is what it came out to. So this setup is much easier than the setup in spherical coordinates, or in cylindrical coordinates. In cylindrical coordinates, we had to figure out what the intersection of the two surfaces was so we could get our region in the xy plane. We had to take into account a region in the xy plane in our limits of integration. Here we can go directly from our region to set up our integral. And this integral is really easy to evaluate. So if you have a region that has spherical symmetry about the origin, spherical coordinates usually are going to be very easy to evaluate. Questions on that one? All right, let's look at one more, and then we'll stop. We want to find I sub z of the solid bounded by hemisphere rho equals cosine phi and 0 less than or equal to phi less than or equal to pi over 2. And the cone phi equals pi over 4. So this is the same cone that we had in our last example. Phi equals pi over 4. The region that we're looking at here, if we just sketch this out, rho equals cosine phi gives me a hemisphere like so. And our cone goes up like this.
Do you know the radius of the hemisphere?
If when phi equals, if I went up like this, when phi equals 0, rho equals 1. So the upper part, the part of the hemisphere that we're looking at, this would be z equals 1.
So are we trying to find what's in between the cone and the hemisphere?
Yes, so we're looking at this region between the cone and the hemisphere. All right, so I sub z is our moment of inertia about the z-axis. So we need to know the distance from the z-axis. So we're weighting our mass by the square of the distance from the z-axis. So we need the distance of our mass unit from the z-axis. So we need to figure that out in spherical coordinates. So the distance from the z-axis, how are we going to represent that in spherical coordinates?
Wait, can you say the question?
We need to figure out the distance of our mass. We're looking at a little piece of mass of this solid,
Right.
and we need to figure out its distance from the z-axis. What's going to be the point? What's going to be the distance of the point from the z-axis?
The,
Theta.
no, the hemisphere.
We just need an expression for the
It could
distance.
be in between the hemisphere and the cone.
So what if we're in the xy plane
It's the big one minus the little one.
and if we're in the xy plane, the z-axis is here at the origin. What's the distance of a point from the origin?
Cross over. Y.
Square root of x squared plus y squared, right? All right. Square root of x squared plus y squared. Pythagorean theorem.
So would this be the square root of x squared plus y squared plus z squared?
So
So
square root of rho.
we're just looking at the distance from the z-axis. So this distance from the z-axis is the same as projecting this directly up from the xy plane. So all we're looking at here is the square root of x squared plus y squared. That's going to be the distance from the z-axis. So we need to write an expression for the distance from the z-axis. So I'm going to call it, I'll just call it d sub z equals the square root. X squared is rho squared, sine squared phi, cosine squared theta, plus y squared is rho squared, sine squared phi, sine squared theta, and if I simplify this, what do I get? Rho sine phi. So my distance from the z-axis is rho sine phi. Did we make a mistake here?
No.
No?
Probably.
No, I think we're good. Rho sine phi. We're good. I just wanted to double check. And let's say our density function is just k.
Wait, how
Is the density still rho, even though rho is something else?
For spherical coordinates, we'll use something else for our density. So our density is k.
how do you know it's k though?
Yeah, I'm just giving you the density function. The density function is
so
just
that
some
would be given
constant.
in the problem.
Right, they would give you the density function. All right, so now we're ready to,
Okay.
and now we're going to set up our integral. Our I sub x or sorry, I sub z. I sub z equals, let's just look at this section in the first octant. So we're just going to look at the first octant and multiply by 4. So we get 4k for our density.
Where are you getting this?
Wait, it's like
It's our
0
density.
to pi half. Oh, that's pi.
For all four countries.
So we're just looking at, I'm just looking at a quarter of this.
Okay.
Everything's symmetrical. I'm just going to look at this quarter that's above the first octant. So 4k. Theta varies from 0 to pi over 2. Phi varies from,
0 to pi fourths.
what is it?
0 to pi fourths.
Pi fourths
No.
on the edge of this cone. We're looking at the section between the cone and the hemisphere.
Pi fourths to
Pi fourths down to the xy plane is,
Wait, why would you go to
90
the
pi
flat
halves.
plane?
because we're only looking at rho, or I'm sorry, phi going from here down to the sphere.
Shouldn't you just go to cosine phi? Or, I mean, shouldn't you just go to the hemisphere?
Yes. So the hemisphere, if I'm on the cone, I'm at phi equals pi over 4.
Right.
It varies. Phi goes from here, 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 and down here at the origin, phi is all the way down at the xy plane. So phi goes from pi over 4 to pi over 2. And that's probably one of the trickier things with spherical coordinates, is that phi starts at the z-axis and goes to the negative z-axis from 0 to pi, from the positive z-axis to the negative z-axis. So phi goes from pi over 4 to pi over 2. Rho, my radius, goes from 0 to what? Cosine phi. That's the radius here on my hemisphere. And my I sub z is a distance from the z-axis squared, rho squared, sine squared phi, times my volume element, rho squared, sine phi, d rho, d phi, d theta. No. So that's my dv. So my integral, I get the integral from 0 to pi over 2. I'm going to simplify this from pi over 4 to pi halves. 0 to cosine phi. Rho to the 4th. Sine 3rd phi. D rho. D phi, d theta.
So the innermost integral, the row one, is that the only one that should have the equation in it?
No, you could have a function for your limits on the second one also.
Okay.
At the end, you're going to end up evaluating for a number.
Okay.
Usually it's going to your integrals, the ones that we'll do are pretty straightforward and pretty easy.
Okay.
So not a difficult integral to evaluate. When we evaluate the Rho integral, we'll go a little further, 0 to pi halves, pi over 4 to pi over 2. We end up with rho to the 5th over 5, integrated on 0 to cosine phi. So we get cosine to the 5th phi, sine to the 3rd phi, d5, d theta, and we have to get our factor of 5 in there. Cosine of 5th over 5. And we left out our 4k here. what I would do here, now we're down to a trigonometric integral. So I have 4/5 k, the integral from 0 to pi over 2, the integral from pi over 4 to pi halves of cosine 5th phi times 1 minus cosine squared phi. I'm taking out a sine squared, and I leave a sine phi, d phi d theta. What's that? Well, now I have u's and my du. Sine phi d phi is my du for my cosine phis.
But you can't use two views.
But if you multiply
If I just multiply through, so I have a cosine 5th, a factor or term with cosine 5th, and a term with cosine to the 7th, and this is my du for each of those. So I get 4/5 k, the again integral from 0 to pi over 2 of, when I do my integral, minus cosine to the 6th of phi over 6 plus cosine to the 8th phi over 8 d theta, and this is evaluated on pi over 4 to pi over 2. And this one, from here out, this is an easy evaluation.
What's the answer?
What's the answer?
No, you tell me.
it's not one.
Give up. It's over.
Yeah, wait, too much math.
This isn't even math, this is just arithmetic.
Okay, then wait, too much math.
4/5 k, integral from 0 to pi over 2. Cosine of pi over 2? 0. So my first, these two are both 0. Minus,
Square root 2 over 2.
But it's to the 6th, so it's like
What?
weird.
Right.
2 to the 6th is like,
right, so minus,
is it 8?
It's a decimal point.
Is it 8?
square root of 2 over 2 to the 6th over 6
Is it
plus square root of 2 over 2 to the 8th
4 or 6?
over 8 d theta.
It's, oh wait, it's 4, is it 10/6? Or wait, no, 2/6, 1/3. I think it's 1/3. That's my guess.
1/3. 4/5 k. I'm just going to say this is square root of 2 over 2
No, just do it.
to the 6th over 6
Oh wait, no.
minus square root of 2 over 2 to the 8th
I give up.
over 8 times pi over 2.
That's what I said.
That's good enough. All right. So the evaluation of this one was a little tedious. What I more wanted to demonstrate was just the setup of the integral, finding our limits. All right. Any questions?
No.
No? Okay. Homework.
Come on, spring break.
Yeah, you got enough time to finish it now, and then you wouldn't have to do it.
Spring break. It's spring break. Let's go tell Miss Johnson that it's spring break. Spring break. She's not here today. Oh yeah.
All right, and so everybody scan your solutions and email them to me by Thursday.